So now we start with the second part of the computation with Matlab. We compute the transition dynamics in a difference equation system. We have now computed the excess burden in partial equilibrium, the excess burden in general equilibrium, but we know that during the transition our variables behave differently and therefore utility is different. So let us look at the result first that you understand what's going on. In the figure presented on slide 43, we see the transition dynamics of the capital stock K, labor L, production Y, consumption C, and tax revenue tau WL, which are equal to government consumption. We start in the old steady state, then there's unexpected change, increase in the labor income tax rate tau L, and the capital stock gradually converges to its new steady state value, and we assume in period 41 the transition is over and we are in the new steady state, so period 40 is the last period of transition. The labor stock is a jump variable, so it undershoots its long run value and then increases to its new steady state value from below, while consumption jumps down and converges to its new steady state value from above. So from these two dynamics of the labor stock, of the labor L and consumption C, we observed that both arguments of the utility function, leisure and consumption, are higher during the transition than in the final steady state, and consequently instantaneous utility is also higher during the transition than in steady state. Therefore, the welfare loss, if we also account for the transition, must be lower. And we want to compute these dynamics. Now, how do we compute these dynamics? It's not a trivial task. It's a difference equation system. We have an initial condition, the capital stock in the initial steady state, and we have a terminal condition, which is the final capital stock in the new steady state with tau L equal to 24%. So this formally is a 2-point boundary value problem, and we have to solve the difference equation system, which is presented in equation 15. So we have a dynamic system in three variables K, C, and L. The dynamics equations are equation 15b and 15c, which are the resource constraint. The resource constraint contains kt plus 1. And we have the Euler condition, where we have substituted the marginal utility of consumption for the Lagrangian multipliers lambda t, so that we have a dynamic equation in Ct plus 1, Lt plus 1, and via Rt plus 1 also in Kt plus 1. So when we substitute Rt for with the help of the marginal product, these three equations are equations in Kt, Lt, and Ct only. Equation 15a, the optimal labor supply, is a static equation, so it only contains variables Ct, Lt, and when we substitute the wage rate Wt by the marginal product, then we also only have an equation in the variables Ct, Lt, and Kt again. So one static equation, two dynamic equations, and for the two dynamic equations we have an initial condition and a terminal condition, and the question is how we solve it. And this is described in Appendix 4.2 in my book Public Economics. We use the method of reverse shooting. How does it work? Let's go back to the slide. We start in period 41, where the capital stock has attained its new steady state value for the labor income tax rate tau L equal to 24%. Then we provide a guess for the capital stock in period 40, and we have to compute labor and consumption in period 40. We do this by using equations 15a and 15b. So we have all the other variables kt, k40, kt plus 1, which is k41, the new steady state value, and we compute ct and lt from these two equations. We also have to substitute here gt by the fiscal budget constraint tau L W LT. So we solve 15a and 15b in period 40 to get ct and lt. Now how do we proceed in the next period? We have the capital stock, consumption and labor for period 40, and we now want to compute capital stock, consumption and labor for period 39. So we then apply again equation 15a, 15b, and now 15c to solve for k39, c39, L39 for given values C40, L40, K40. So we solve this difference equation system 15. This provides us with new values C, L, and K for period 39. And we continue to use this dynamic system to compute the values in period 38 and so on up to period 0. And then we compare our value for K0, our capital stock in period 0, with the value of the initial steady state value of the capital stock. And if it's equal, we are done. If not, we have to respecify a new value for K40 and try again until we have found a value of K40 that implies the initial capital stock K0 equal to the old steady state value. So this is a nonlinear equations problem. We want to find K40, and the equation that it returns is the found value of K0 minus K star, the value of the capital stock in initial equilibrium. Within this nonlinear equation problem, we have to compute the transition dynamics and have to solve iteratively for the dynamics, again, solving a nonlinear equations problem. So we have a nonlinear equations problem nested within the nonlinear equation problem. And this is the outer equation is find K in our Matlab program, and the inner nonlinear equations problem is called find LCK. So let's switch back into our computer code. Let's go into the Matlab program. And continue our iteration. So in line 120, you find a short description of what we do. Step 5, computation of the transition, outer loop over K40 in the final period of the transition. Therefore, we have to solve the nonlinear equation function find K. And in the inner loop, in the first step, we compute L40 and C40 for given K40 and iterate backwards in time until we have found K0. So let's execute the commands one by one. We first store the final steady state values in the parameter K final, L final, C final, G final. Provide as an initial guess a small perturbation of the new steady state K new 1. We increase it by 0.1%. So we know that we approach this new steady state value from above, so we should increase the value, and here we do it with a small amount, by a small amount, 0.1%. Now for didactic reasons, I have included this line that we execute find K so that we can step in and analyze the function find K, which provides the outer loop. So for given initial value K40, it finds K0 and compares it to K star, the initial steady state value. The variables in period T are stored in K young, C young, and L young, respectively, and the variables in period T plus 1 are stored in K old, L old, C old. The solution is stored in the matrix X time path, which saves the capital stock the labor stock, production, consumption, let me step out, consumption, government expenditures, which are equal to tax revenues, and the period in row NT plus 2 here for the final row, period 41 when we are in the new steady state. In period 0, when we are in the old steady state, we save the variable values in the first row of the matrix X time path for K, L, production, consumption, tax revenue, and period 0. Now we have to compute the labor supply and consumption for given value K40. So as initial guess, we use, of course, we can use the old steady state values, L old and C old. Oh, sorry, these are the new steady state values, L old and C old, and solve the first order condition FOC1, where the two equilibrium conditions are stored. The first equilibrium is the first order condition with respect to labor, and the second one is the budget constraint. And this provides us with labor 40 equal to 0.2995, so in period 40 this is our labor supply, and consumption 0.2998, and these values up to 4 digits are the same as the new steady state values. And we store the values of the endogenous variables in period 40 in X time path. And now we get into step 5.2, where we compute KT, CT, LT iteratively by going backwards in time. So our old guess is saved in the variable x0, and this is allocated, the old values K old, L old, and C old are saved in the parameter vector, and we solve the condition, the dynamic equation, find LCPK for the initial value x, which are the old, the next period, capital stock KT plus 1, labor LT plus 1, and consumption CT plus 1, and for the parameters par, which are parsed to the function FLCPK. So let us go to function f, find FLCPK. K, labor, and C is the initial guess here for the variables in period T. The variables in period T plus 1, K, L, and C are stored in the parameter vector par, which is the second argument of this function. And they are assigned to the variables K1, labor 1, C1. We compute wages, interest rate, and the government expenditures with the help of these variables. And our three dynamic equations in KT, LT, and CT are specified as y of 1, y of 2, and y of 3. So y of 1 is our first order condition with respect to labor, the static equation. Y of 2 is our budget constraint or our resource constraint, and equation y3 is our Euler equation, and this is solved in with the help of a nonlinear equation solver. And for example, we find the solution 1.2873, 0.2996, and 0.2998 for capital stock, labor, and consumption in period 39. We store these values in X time path and make the variables K young, L young, C young in iteration T, assign it to K old, L old, C old in iteration in period T minus 1. And we continue to do so until we have find the whole transition. And let us jump ahead. when we find the O transition, we return in this procedure K0, which is then assigned to the variable K young, minus the old steady state value K star. So let's step out of this procedure here and present to you and press any key for the pause statement, clear the screen, and show you and search for the solution by solving this nonlinear equation system. So the syntax of this command, fsolve, which finds the solution of a nonlinear equation system, is the following. You specify the function with an @ sign, chapter 5 find k. The function has two arguments, k0, which is our guess for for the capital stock in period 40, K40, and the parameter vector with the tax rates, the parameter for beta, alpha, and so on. We provide an initial guess of K40, which is stored in the variable K initial, and we tell fsolved with regard to which argument you have to find he has to find the zero. Sorry, the zero. So with respect to the first argument, which is K0, the capital stock. This is very convenient, so we can pass a parameter vector to this function and use a different argument for it. So fsolve knows that it only has to find the zero with regard to the first argument, K0. And the solution is stored in K solution. We find, this takes a second here. So we find that this solution here is 1.2862. So that's the value of the capital stock in period 40, K40, which implies a dynamic of the capital stock when we iterate backward in time, that the capital stock in period 0 is equal to K star, our initial steady state capital stock. And now we changed the two parameters display and utility to 1, so that when we execute the function find k, chapter 5.3 find k, that the solution are displayed and lifetime utility is computed. So let me get into this function here again to show you what's new now. We do the same iteration that I described to you in a second, and let's go to line 264, so continue our iteration. Now the value of display is set equal to 1, so the solution is the figure will be displayed. Let me just skip through this. I have to press any key so that you have the solution displayed in figure 1 here. And now we have also set the parameter utility to 1 so that the lifetime utility is computed. So what's lifetime utility in the old steady state? Well, instantaneous utility is constant. We always have consumption C star and labor L star and the parameter vector par. And this provides us with lifetime utility, well, instantaneous utility divided by 1 minus beta. It's just a geometric series. For the case that consumption changes, we have to use the consumption, the labor path for the first 40 periods that we computed. This is done in the loop between lines 933 and 297. And let's now jump to line 297. And then we have to add the utility for the remaining periods of the lifetime of a household. So from period 41 through infinity, and this utility is given by this expression here. So we discount the lifetime utility for someone born in period 41 would be this one, and we have to discount it by 40 by beta to the power 40 to get the lifetime utility for the case of the of a change to the labor income tax rate equal to 24%. And now we can compute the consumption equivalent change again from comparing lifetime utility under tax policy 1 and 2, under tax policy 23% and 24%, and compute the consumption equivalent changed by 1.073%. So let's step out of this procedure here again, press any key, and we are done with our program. So let me get back into our editor. So this terminates our computation with the help of the Matlab program, chapter 5, welfare tau L. And let me conclude with one comment. Why have we solved this problem with reverse shooting? So let me get back into the slides for this reason. And you may wonder, why did we apply reverse shooting? So starting in period 40 and working back in time until period 0. Why didn't we start in period 1 and worked forward? So we have K0, and as an initial guess, we might have started with a value of K1 and then iterated forward and compared K41 with the new steady state value. Well, if you consider our dynamic equation system 15, you will notice that this is not possible. So remember how we proceeded in the case of reverse shooting. We started in period 40 and had to compute consumption and labor in period 40 by using equations 15a and b. Now the same logic applies to the case if we solved it forwardly. So in period 1 we had to compute consumption and labor from these equations 15a and 15b. But then you notice that not only K1 enters this equation, but also K2. So, and we do not have this value K2. So our procedure breaks down at this point because we always need to know the capital stock next period in order to solve for consumption and leisure this period. And therefore the only doable way, the only operational way, is to use reverse shooting and starting in the last period of the transition. If we didn't have endogenous labor, this problem would be less severe. But with endogenous labor, we cannot help but to use reverse shooting. So I hope you enjoyed this video. And if you have any remaining questions, or have problems with the source code, please just send me an email. And of course, it might take some time until I get back to you. But eventually, you will hopefully get an answer from me. So I hope you enjoyed this. Liked my book on public economics, and in particular the insight from chapter 7.3 on labor income taxation and the distortionary effects of labor taxes on welfare consumption and labor supply.